Hi everyone, I'm Qinxun. I'm a PhD candidate at University of Utah. Today I would like to present my recent work on a new geometry proof for dark energy, kinematic lensing ratio. So as you all know, recent exciting measurement of BAO by the DESI collaboration found a deviation from lambda CDM, and combining these with supernova and CMB, we can tentatively interpret this as evidence of dynamical dark energy. You can see more introduction in Enrique and Kusha's thoughts on this result. A good advantage of the two of the three methods using this constraint is that both supernova and BAO measure the distance redshift relation. These are say purely geometry measurement. We don't need to worry about the say modeling the structural growth. There are lots of uncertainty in this modeling from, for example, baryonic physics or some kind of new physics like screened with modified gravity. Some of these physics only affect the structural growth, but not the geometry, the expansion history. So geometry measurement can get rid of these complex physics and make a clean and robust measurement on the background evolution. But supernova and BAO are limited by their available redshift range. This result in a degeneracy between the constraint on dark energy parameters and the omega m. This kind of limited their constraining power and property of dark energy. If we can break this degeneracy, introduce say additional constraint on omega m, we can improve the constraining power by a lot. So that's why we want to use weak gravitational lensing. It is one of the four methods recommended by the Dark Energy Task Force. Uh, we can make those measurements based on imaging surveys, for example, Euclid, Rubin, and Roman. Basically make use of the shape distortion of background galaxies induced by the gravitational field of foreground galaxies and large-scale structures. People already make these make use of this method to put strong constraint on the amplitude of structure growth, the SA parameter. This constraint from dark energy survey is on already comparable with CMB, which is very exciting, but it is hard to use reclaiming for constraining dark energy because, as I mentioned earlier, you need to model those baryonic effect and uh, yeah, make use say model that's about baryonic physics. Otherwise, you need to make a straight scale cut and remove lots of information. So to understand weak lensing, we can take a closer look into the weak lensing observable. Here I take the tangential shear gamma t as an example. It can basically consists of two terms. This term is the length mass distribution or structure growth term. And we also have a geometry factor which consists of only distance observables. The weak lensing observable alternatively encode both information but mix them together. So that uh, if we want to extract the geometry information, uh, that would be a good news for probing dark energy. Why? That's because we can learn this lesson from the galaxy clustering. So these are the galaxy two-point correlation function. They encode lots of different information, including the BO peak position, redshift space distortion, L-Kopaczinski effect. And if we go to small scale, they also have information on galaxy halo connection. In the DESI BO measurement, people use templates to feed the signal and extract only the peak of the BAO and convert this into a distance redshift measurement. This is purely geometry. And we can use this to do model agnostic constraint or reconstruction on dark energy properties. That's helpful. So can we do a similar extraction to weak lensing observables? The answer is yes. So this is the idea of shear ratio proposed by both Nash Zhang and Tony Taylor. So the key idea is to make use of the same length galaxy, but two different sample of source galaxies at different redshift. Because they share the same length mass distribution term, we can take the ratio of these source at different redshift, and the mass distribution does cancel out and leave only a pure geometry factor. People have been proposing to use this as a dark energy proof, but there are also some challenges when we really try to apply this to observation. The root reason is that weak lensing is weak. It's only a few percent of the galaxy intrinsic shape. So we would need to stack over a large number of galaxies. Uh, so as an example, if the unlensed uh, length distribution of intrinsic shape is a circle, we can the weak lensing induce a preferred direction, and if we stack over say over that direction and make the weak lensing measurement, we can find an eclipse. So the difference between the eclipse and the circle is the weak lensing shear. But what if these intrinsic shape of galaxies are not independent? So these two assumptions result in two observational challenges. That's the error of photo Z of photometry redshift. We need to make precise calibration of this photo Z. Otherwise, our constraining power on cosmological parameter will be fairly limited. And also, the intrinsic alignment of galaxy shape induce a non-geometry turn in shear ratio. It makes us much harder to model those signal and also contaminate our signal. To get rid of this problem, we introduce the kinematic lensing method into shear ratio. So kinematic lensing is also not a very new idea. It was proposed by Blaine 2002 and collaborator 2002. The idea is to infer the intrinsic galaxy shape from kinematic observation. So two galaxies can have exactly the same image but fairly different kinematic structure or rotation curve. That's because one of them is inclined and the other is sheared by the weak lensing. But so if we can measure this kinematic structure of the galaxy, we can uh, disentangle, you can break the degeneracy between the inclination and weak lensing, and infer the intrinsic shape of galaxies, um, make a precise measurement of the shear ratio directly. So this can reduce the noise of recleansing in say by a factor of roughly 10, depending on the signal to noise of kinematic measurement. Combining the idea of shear ratio and kinematic lensing, we thus propose the kinematic lensing ratio method or KiLeR. So we have lots of advantage. Some of them comes from shear ratio, where we can make purely geometry measurement, and they are insensitive to the baryon effect. We don't no longer need to do a couple of hydro simulation to do the calibration. And also we have advantage from kinematic lensing because we now only need a small number of galaxies. We can use a small spectroscopic sample to do the measurement. We don't no longer need to worry about photo Z error. And also by reconstructing the intrinsic shape of galaxy, we uh, do not need assumptions on the intrinsic alignment. So this get rid of two annoying systematic in weak cleansing. So with this robust and clean cosmological proof, we need to see whether it is powerful enough to be useful. So we make a forecast based on the upcoming Roman Space Telescope. We use a lens galaxy sample from DESI Bright Galaxy Survey and Luminous Red Galaxy. They are kind of typical example of ground-based fiber spectroscopic surveys. And we will get the similar sample in larger Roman footprint from the foremost. And for the source sample, we assume the Roman Graydon Slither spectral sample. This is the detailed parameters are adapted from a previous Roman kinematic lensing forecast by Xu and collaborators 2023. They estimate the effective number density of kinematic lensing sample by selecting the late type high signal to noise on emission line galaxies from a mock galaxy sample, and they also require the size and magnitude of these galaxies to be suitable for recurrent measurement. And we use some state-of-the-art tools using cosmological analysis of stage 3 surveys to make out our data vector, estimate the covariance, and run the Monte Carlo constraint. So here are our mock data vector and covariance. The left panel from top to down, we have increasing redshift of the length sample. From left to right, we have increasing redshift of the source sample. The red dashed lines are our input true cosmology, the W0 WA, and black dotted lines show our standard cosmological model constrained by Planck 18. So from these error bars, we can tell that our model can distinguish these two different cosmology. But as shown in this right panel, most of these points are highly correlated with each other. So we need a full cosmological constraint from Monte Carlo to quantify the constraining power. So we run the MCMC and estimate the posterior distribution and quantify the constraining power by figure of merit. Compared to the state-of-art constraints from CMB, BL, and supernova, we found that KiLeR can replace any one probe of this combination and get a similar or better constraint. So this is very important because we can test the significance of this dynamical energy evidence independent of any one of the three probes. And if we combine KiLeR with all these three, we can get a twice better figure merit. So this figure mirror is enough to distinguish this current best fit on WWA from the lambda CDM with more than 5 sigma. We also test how robust our probe is against systematics. So the most important systematic error we test is the multiplicative bias. It kind of include most of the actual physical uncertainties, including uh, the the diversity of kinematic structure of galaxies, all this propagating to this multiplicative bias. parameter. And we assume a level that's comparable to recleansing measurement. And we found that after marginalize over this parameter, we still have a fairly good constraint. This mild figure mirror degradation is even say almost disappear after we combine with other cosmological probe, for example, the BAO. And the reason why we are so powerful on this KiLeR method is because the KiLeR on Roman sample is able to prove the expansion history at high redshift, so from zero point 0.6 to higher than redshift 2. So this precise constraint at high redshift is able to put a tight constraint on omega n and break the degeneracy between omega m and dark energy parameters in the BAO or supernova constraint. And this also means that KiLeR method on Raman sample is sensitive to neutrino mass. If we look beyond of the Raman telescope, there are more further opportunity of this method. Euclid and China Space Station Telescope will survey much wider area, and especially CSST can make slickler spectral measurement in optical bands. It allowed us to extend our sample uh, to redshift below zero point 0.6, but their spectral resolution are lower, so it makes the kinematic lensing measurement much harder. And we also have some challenges. So to make realistic measurement, we need to have mock data and measurement pipeline. They can provide us a better estimate of shape noise and number density. And we need to figure out a good statistical estimator of the signal. And there are lots of astrophysical systematics to be understood. And we need to figure out whether the current weak lensing shear calibration method was on kinematic lensing. Uh, but this also means lots of opportunities. So, in summary, we propose a new method that's clean and robust against lots of weak lensing uncertainties in both measurement and modeling. And we show that with Roman data, it can be powerful. It's twice better than the current constraint. There are lots of work to do before we really bring this measurement into real observational data. Thank you.